Hello and welcome to Subfactors. So today we'll have a more specialized final lecture. It's going to be a bit philosophical about what is going on right now in subfactor theory and quantum groups inspired from subfactors. I mean, operator algebraic somehow quantum groups and subfactors. So it's going to be mostly philosophical. I mean, really very tough research, but I think with this 5 lectures before, if you just download the slides and look a bit at them, you can understand a bit what's going on in this lecture. So let's find it first. Here we go. So factors of small index and big index. So first seeing why small and big and not arbitrary index. Well, this is what's going on actually. There are two directions of research somehow, small index and big index. So we'll see all this. So let's start with some, just a short summary. So this is the Jones theorem, part 1 and part 2. If you take a subfactor, finite index, by basic construction, you have this Jones tower. The Jones projection generates a copy of the temporally Lie algebra. That's all stuff from the 80s. And more recent stuff from the 90s is that the planar algebra structure of the temporally Lie algebra, which is just, I mean, we have diagrams, so we can glue them like this in many senses, extends into a planar algebra structure of on the space of high relative commutants. So you see, I take the commutant of the A0, the subfactor, the initial one, into all these guys obtained by basic construction. These are finite dimensional algebras if the index is finite. They contain the temporally Lie algebra. That's not hard to check either. And the point is that since you have P, this thing which is somehow bigger but still finite dimensional things, inside there is temporally Lie, and temporally Lie are diagrams. The theorem says that P, which is bigger, the elements are not exactly diagrams but behave as diagrams. They form a planar algebra, meaning that whenever you have a box with small boxes, you can plug in elements here and get an element on the output box. It's somehow, that's the idea. These commutants are not formed by diagrams, or at least we don't know how to say that, but they behave like diagrams. Everything that you can do with diagrams, you can do it with these commutants. Now, the point of these commutants, also importantly, is that they classify the subfactor and the suitable assumptions. So the previous slides was all Jones. Now this is all Popper, more or less. So the subfactors are infinite depth, somehow meaning that the quantum group acting there is finite, are fully classified by the planar algebras. More generally, in the amenable case, also they are fully classified by planar algebras. Now, in general, this is not exactly true, but so we know that any subfactor possesses a planar algebra. You can prove that the converse is true too. So any planar algebra possesses a subfactor. But the correspondence is not bijective, and this subfactor construction uses actually some kind of pre-product thing. So it's inside the pre-group factors, more precisely following Popper and Shliak-Tenko with and others, Gion and Jones too are involved. You can do it with the law of F infinity. So this is very nice, but as a main question, what are the planar algebras of the subfactors of R, the Murray per finite factor? So this is not really covered by all these things. So in the amenable case, yeah, we know, but the amenable planar algebras are in correspondence, but well, no, not really, not in the amenable case. Well, it's a bit complicated, so that's the question to be solved. Now, one more thing, we need invariants now in order to talk about this planar algebra source of factors. And the main invariant, it comes in 3 flavors. It depends on your taste. So, because there are 3, you have the good, the bad, and the ugly. So, following most of people, the good invariant is the principal graph. You take the Brattray diagram, you erase the reflections, and that's your invariant. And it's very good, wonderful. Then the bad is the Poincare series, which is obtained by summing these dimensions of pk with zk as now as coefficients. And the ugly thing, which is probability, we don't want that, is to consider a spectral measure having as moments these dimensions. There's the majority, the minority, and I belong to this minority. Says that it's exactly the opposite. So the good invariant is the spectral measure, the bad is the Poincare, and that gives the principal graph. So is there any kind of agreement that can be reached? Probably no, but the common thing is that for both schools, the bad thing is the Poincare series, right? It's in the middle, and actually, Von Jones uses the Poincare series. So we're probably both wrong. Well, anyway, that's just for jokes. So anyway, yeah, in this talk, it's going to be like this: the good is the spectral measure. So I was always, when talking about invariants, I always only compute the spectral measure. I won't bother with the Poincare and the principal graph. Well, not really, because we have graphs here. Let's talk about small index first. So index less than 4, you have this Jones index restriction coming from the existence of the Hilbert representation of TL. And well, you have the n must be the square norm of a graph. You have an ADA classification result. Now, it's a bit hard to explain, but in index 4, where you have quantum groups for the spin models of factors in this very particular case, what we need here is to classify the quantum permutation groups on 4 points. And this can be done independently on this factor business. So S4 plus is actually a twist of SO3. So you get twists more or less of the AD subgroups of SO3. So this is nicer, but it's very particular. I mean, it's really spin models of factors and at index 4. Now, when you see this, you say, the story is over at index 4, but is it? Well, yes, but there are some more things which can be done. So let's compute first the invariants. In general, in the Subfactor context, well, you have to start with the graph, maybe, or Poincare series of graphs are AD. Poincare series, the coefficients count loops there, so count and get it right away. And the spectral measure can be recovered by still this inversion. At NS 4, well, you have quantum groups on there. What's most natural is to compute the law of the character. That's your measure. And then you get the Poincare from that by integrating in the graph if you want. So these are the invariants. Now, there's no need for giving them to you because actually this can be upgraded. So Jones discovered that if you do this manipulation of Poincare series, you get something with positive coefficients. That's his deep result in the annular structure of Subfactors paper. It's called the Theta series. And I played a bit with this with Dietmar Bisch in index less than 4, which is somewhat trivial. And we discovered that at the level of spectral measures, exactly the same manipulation blows up the measure, which is real. And then you circle, and the formulas are extremely simple. So it's just sums of measures on roots of unity. It's very, very nice. So this is the final result, I think, on the invariants. That's in my paper with Dietmar, definitely index less than 4. Of course, it's philosophical. I mean, the big thing was to classify before we said that's the big thing, many people involved. So this is just having some fun afterwards. But it's not that fun. I mean, it's a bit serious, right? This thing with Jones involved and me and Dietmar, I think the formulas with roots of unity are the final thing there. Now, small index but bigger now, so things become serious here. If you want to get up to index 5 and a bit after 5, it's terribly complicated. You have to use very advanced planar algebra techniques. This was done by Scott Morrison and the others, and they reached to a classification. It's very tough. I mean, many papers recent, so it's one of the main results in mathematics. I mean, things are classified from time to time. Guys classify like simple algebras or complex reflection groups or whatever. And this was, I think, the big classification result in mathematics in the last decade. Yeah, very, very tough results. Now, once again, well, in this index range here from 4 to 5 and something, we have in the integer value, that's 5, right? So there we have quantum groups or spin factors. We can try to classify the quantum permutation groups. Well, actually, when Julien Bichon is a bit about this, we don't know how to do it. So we had to wait for these guys to be over with their classification, Morrison and the others, and import the result. And yeah, you can classify these things definitely. just take the results. There's just some twisting work to be done, which is actually not fully done yet. There's still some things to be done there. In the transitive case, it's done. Well, anyway, modulo some things, it's done. Now here there are many questions in small index which are open. So first of all is that what's the correct blow up of the spectral measure in index 5? More generally in this Morrison and the others understood index range, that's not known. Available for the Huggy group or Huggy group aside as factors, we don't know how to do that. I remember I we did that with Dietmar back in Toulouse long ago, and I couldn't find something for Huggy group. But I think that should be possible. I don't know. And yeah, Evans and Pugh worked a lot on these questions, but I don't think they have a clear answer for Huggy group as far as I know. So I think this is open. Now, question 2, in quantum groups, so we know what are the subgroups of S4 plus, also S5 plus. In most cases, there's no thing in between S and Sn plus, so problem now at SE6 how to do that in general. So that's a big problem in quantum groups, very related to all this. Now, third question, in index 6, you cannot classify also factors because there are uncountable families, things like that. I mean, 6 is 2 times 3, and you can do a lot of things with that. So there's no hope for classifying, but what's the natural extra assumption to be added in order to some factors to become classifiable? And I don't know. I mean, well, like all these guys, Morrison and for the others, Snyder, Peters, Pennis, James Tanner, Izumi was also involved, Von Jones himself. Yeah, many people, they have all these kind of assumptions on a factor that you can put, but I still understand a bit outside of this story. I'm rather into big index, so I still understand from what they're doing, what their plan is at index 6, what's the assumption that they have in mind. I'm sure they have some, so wait and see. Now, let's talk a bit about big index as well. So this is important. I mean, if you look at simply algebras, comparative action groups, or whatever other classification results, for these serial objects and exceptional, serial and exceptional. So all this small index work, somehow it's more about exceptional things. I mean, Huggy group, Asada, Huggy group, all that, they're rather exceptional. So all these things I was talking about before, well, they're important, but it's not exactly looking at serial factors. So I try to understand that. By serial, I mean one for each n, right? At least for each n integer. It's not very clear what this should mean, but that's the smallest requirement, to have a subfactor at any n. So for that, in the quantum group context, let's take any integer, must have a quantum group at any n. And well, if you think and do Tanaka and other things, you reach to this notion of easiness. That well, there's no story here. It's in a paper of mine with Spiker following previous work with Bishon, Collins, and others. So quantum group is called easy if the Tanakian category is spanned by diagrams. Yeah, it's implementation of diagrams. So that's it. Well, as basic examples, ON plus, UN plus are all easy coming from. So from ON, UN is just Brouwer. I mean, it's pairings and matching pairings. And for the free version, it is free Brouwer, non-crossing pairings. Why? Because the free version, you don't want AB to BA, right? You remove commutativity, and AB is BA diagrammatically means the crossing. So we want to remove the crossing, and that's why you get these non-crossing pairings. And the measures now, well, you can compute them right from the pairings here. They are for n, it's well known, it's normal. Here it's complex normal. And here you obtain the free versions of the normal laws. These are the Wigner semicircle and the Voigt-Plescu circle. And goes to infinity. So these are very basic things. Now, let me tell you also more complicated now. So we can enlarge this diagram we had before with reflection groups, octahedral and complex reflection groups. Once again, they're all easy. At the level of measures, you get this nice diagram for free probability. So once again, this is something that we discussed already: normal, complex, semicircular, and circular. And on the left, you get this Bessel laws, real and complex, and classical and free, which are very important for free probability. I mean, these are the 8 main measures of free probability somehow. and also the vertical arrows of the Berkovich pattern bijection. So it's very conceptual. So you see here, I mean, if you do graphs with or Poincare series, you won't reach to this cube here, which is extremely important. So that's why it's better to do it with measures, reach to this kind of things. Okay, now of course there are many questions now, and these are just very basic things. So if you want to extend that, there are many problems. Classification of daisy quantum groups, of course, that's what Moritz Weber and the others do now in Zarbook, and various extensions of daisiness theory. So countless ways of extending this. In particular, a subject which things are quite advanced are the super easiness. That's something I did with Skalski long ago. It's understood. I mean, easiness, but the superstructure I did on CN. And on the other hand, queasiness. I mean, queasiness with Q is plus minus one is also understood. The problem is that these things are not unified yet into a kind of super queasiness theory. On the same line, of course, you have all this work of Amaury Frelon and the others, partition quantum groups, and that also needs to be understood and unified somehow. So that's one direction, but the other direction, which is important, is to cover also the non-commutative tori. So getting back to the big diagram before, all these guys have tori here, which are free group duals or duals of binary groups in the free case. And these tori are not exactly subject to this Berkovich-Pata bijection, but rather to the free Meixner bijection for free probability. So it's a big problem there, how to unify BP and free Meixner. So all this, finally, the union of all these problems, which are of course of interest, is about, for Subfactors theory, it's about classifying serial Subfactors. It's a mixture, as you see, of quantum groups, non-commutative geometry in relations with history and all that. And free probability, of course, it's everywhere, especially non-commutative geometry doesn't. In relation with the last problem in the tori and these quantum groups, you can also throw in some spheres or that homogeneous spaces. So there is a problem that of understanding what's an easy manifold somehow. So including the tori, it's not fully group theoretical. There's some geometry there too. So finally, you see in this big index business, Subfactors are not alone. I mean, there are parts of a scheme involving quantum groups, non-commutative geometry, free probability. So here's my picture. These are operator algebras, old stuff. System algebras for Neumann random matrices Lie group. And these are more modern things. Non-commutative geometry, Subfactors, free probability, quantum groups. That's all the picture of operator algebras. So their interactions are here and the hot stuff is here. And well, if you want to understand what a serial Subfactor, I think that's your picture. I mean, you're not alone here, you're somehow here. So that's it. Now the final question. Yeah, what about the hyperfinite factors? So yeah, in all these things we're talking about, there's not so much about hyperfiniteness, it's pure algebra. So this is the big question that I already told you about in the beginning. Yeah, not to do with hyperfinite factors. I don't know. So this is it. Hope you like it, guys, and well, have fun with Subfactors.